What if everything you see right now, your hands, this screen, the air filling your lungs, every star burning in the night sky, every galaxy spinning silently billions of light years away, what if none of it should exist? What if the universe, by every law of physics we have ever discovered, should have wiped itself out of existence before a single atom ever had the chance to form? This is not a thought experiment. This is not a philosophical riddle. This is the single most terrifying and humbling unsolved mystery in all of science. And the deeper you go into it, the more your mind starts to crack open in the best possible way. Let's go back, way back, further than you've probably ever tried to imagine. We're talking about the very first fraction of a second after the Big Bang. Not a second, not a millisecond. We're talking about 1/10,000,000th of a trillionth of a trillionth of a trillionth of a second after the universe began. A moment so incomprehensibly small that there is no word in any human language that does it justice. At that moment, the universe exploded into existence in an event of pure, raw, incomprehensible energy. Temperature beyond anything your brain is wired to process. Density beyond anything that exists anywhere in today's universe. And out of that explosion, two things were born: matter and antimatter. Now stay with me here, because this is where it gets beautiful and terrifying at the same time. Matter is what you are made of. Protons, neutrons, electrons, the tiny building blocks of every single thing you have ever touched, seen, tasted, or loved. Antimatter is its mirror twin. An antiproton has the same mass as a proton, but carries the opposite charge. A positron has the same mass as an electron, but spins with opposite properties. They are perfect reflections of each other. And here is the thing that physics tells us with absolute certainty. When the Big Bang happened, matter and antimatter should have been created in exactly equal amounts. For every single particle of matter, one particle of antimatter. Perfect symmetry. Perfect balance. And you already know where this is going. Because if that perfect symmetry had held, if the universe had truly created equal amounts of matter and antimatter, they would have found each other. Every particle of matter would have collided with its antimatter twin, and they would have annihilated each other in a flash of pure energy. Every single one. Every proton canceled. Every electron erased. Every neutron dissolved into nothing. The universe would have destroyed itself before it ever began. There would be no stars, no planets, no galaxies, no atoms, no you. Just a vast, dark, cold, perfectly empty ocean of photons, particles of light, drifting through an endless void with nothing to illuminate and no one to see them. But here you are, reading this, breathing, existing, which means something went wrong. Or maybe something went incredibly, miraculously right. Because somewhere in the first heartbeat of the universe, the symmetry broke. Somehow, for reasons that no physicist on Earth can fully explain even today, matter won. Not by much. The numbers are almost insultingly small when you look at them. For every 1 billion antiprotons in the early universe, there were 1,000,000,001 protons. For every 1 billion anti-electrons, there were 1,000,000,001 electrons. That tiny, razor-thin margin of one extra matter particle for every billion pairs, that was enough. The antimatter and the matter annihilated each other in their billions, and what was left, that single leftover particle out of every billion, became everything. Every star, every planet, every ocean, every mountain, every human being who has ever lived on this earth. We are the survivors of the most catastrophic war in the history of the cosmos. And nobody knows why we won. Scientists call this the baryon asymmetry problem. Baryons are a family of particles that includes protons and neutrons, the heavy stuff, the stuff that makes up the core of every atom. The asymmetry refers to the fact that there are more baryons than antibaryons in the observable universe. And the problem is that the standard model of particle physics, the greatest, most tested, most verified theory in the history of science, the theory that has predicted experimental results to a precision of 1 part in 10 billion. That theory says this should not have happened. The standard model predicts that matter and antimatter should have been created in exactly equal amounts. But they weren't, and the model cannot explain why. Think about what that means for a moment. We have built the most precise scientific instruments in human history. We have accelerated particles to within a fraction of the speed of light inside tunnels stretching for kilometers beneath the ground. We have smashed protons together with energies that recreate conditions from the first moments of the universe. We have detected gravitational waves from colliding black holes a billion light years away. We have photographed the very first light that ever crossed the universe. And yet, the most fundamental question of all, why does anything exist, remains unanswered. That should shake you. That should fill you with a kind of dizzy, electric wonder that makes you feel tiny and extraordinary all at once. Let's talk about antimatter in the real world for a second, because it's not just a theory. Antimatter is real. We make it. Right now, at CERN in Geneva, Switzerland, inside the most sophisticated physics laboratory ever constructed, scientists are creating anti-hydrogen atoms, complete antimatter atoms, trapping them in magnetic bottles, and studying them with extraordinary precision. Because here is what they're looking for: any difference, any tiny measurable difference, between how antimatter behaves and how matter behaves. The laws of physics, as we currently understand them, say there should be no difference. An antihydrogen atom should emit exactly the same spectrum of light as a hydrogen atom. It should respond to gravity the same way. It should tick with exactly the same quantum rhythm. But if there is even a tiny, microscopic deviation, if antimatter falls slightly differently or vibrates at a slightly different frequency, then we would have found a crack in the symmetry. A clue, maybe the beginning of an answer to why we exist. So far, every measurement has come back maddeningly identical. Matter and antimatter, as far as we can measure, behave exactly the same, which deepens the mystery, which makes the question louder. Which means the answer, if there is one, is hiding somewhere we haven't looked yet. And that is both the most frustrating and the most exciting thing about being alive in the era of modern science. Now let's go deeper. Because there's a concept in physics called CP violation. C stands for charge conjugation, which basically means swapping matter for antimatter. P stands for parity, which means flipping the spatial coordinates, replacing left with right, up with down, forward with backward. If the laws of physics are truly symmetric, then any physical process should look exactly the same if you swap matter for antimatter and flip the mirror. For a long time, physicists assumed this was absolutely true. Then in 1964, two American physicists named James Cronin and Val Fitch discovered something that shook the entire field. They were studying particles called kaons, strange particles that exist in both matter and antimatter versions. And they found that the two versions did not decay in exactly the same way. The symmetry was broken. It was tiny, almost too small to see, but it was real. Cronin and Fitch won the Nobel Prize in Physics for this discovery in 1980, and it remains one of the most profound and unsettling results in the history of science. But here's the thing that physicists lose sleep over. The amount of CP violation that has been observed in kaon decay, and later confirmed in particles called B mesons and D mesons, is real, but it is nowhere near large enough to explain the matter-antimatter asymmetry we see in the universe. The numbers don't add up. We have found a crack in the symmetry, but it's a hairline fracture when we need a canyon. The observed CP violation explains only a tiny fraction of why matter won over antimatter, which means there must be another source of asymmetry out there. Something we haven't found yet. Something bigger. Something that is likely waiting to be discovered in physics beyond what our current standard model can describe. Some physicists believe the answer lies in neutrinos. Neutrinos are the most ghostly particles in the universe. They have almost no mass, so little that for decades physicists thought they were completely massless. They carry no electric charge. They interact with matter so weakly that right now, in this very moment, hundreds of trillions of neutrinos are passing through your body every single second, and you feel absolutely nothing. They pass through the entire Earth as if it were barely there. They are the universe's most antisocial particles, utterly indifferent to everything around them. But they might hold the key to our existence. There is a phenomenon called neutrino oscillation. Neutrinos come in three varieties or flavors: electron neutrinos, muon neutrinos, and tau neutrinos. And as they travel through space, they spontaneously change from one flavor to another, cycling through their identities in a quantum dance that has no parallel in ordinary human experience. This was itself a Nobel Prize-winning discovery. But the really exciting part is this: there is evidence, not yet conclusive but growing stronger with each passing year, that neutrinos and antineutrinos oscillate differently. That the matter version and the antimatter version of these ghostly particles do not behave in exactly the same way. If this is confirmed, if neutrino CP violation is real and large, it could be a significant piece of the puzzle. It could help explain why matter won. The experiment at the forefront of this search is called T2K, which stands for Tokai to Kamioka. In Japan, physicists fire a beam of neutrinos from a facility on the coast of Japan through 295 kilometers of solid rock to a giant detector buried deep in a mountain. The detector is filled with 50,000 tons of ultra-pure water, surrounded by thousands of light sensors waiting to catch the faintest flicker of a neutrino interaction. And in 2020, the T2K collaboration published results showing a significant hint of CP violation in neutrino oscillations. Not a confirmation, not yet, but a tantalizing, heart-quickening hint that sent ripples through the physics community. The next generation experiment, called Hyper-Kamiokande, is even more ambitious. A detector holding 260,000 tons of water, with the sensitivity to either confirm or rule out leptonic CP violation within the next decade. But even if neutrino CP violation is confirmed, and even if it turns out to be large, there are physicists who believe it may still not be enough to fully explain the baryon asymmetry. The numbers may still not quite add up, which leads us to even more exotic territory. Theories that go far beyond the standard model, into realms of physics that have never been experimentally confirmed, but are mathematically compelling enough that thousands of the world's greatest minds have devoted their careers to exploring them. One such theory is called leptogenesis. The idea is that in the very earliest moments of the universe, at energies so extreme they cannot be recreated in any laboratory, certain super-heavy particles, far heavier than anything in the standard model, particles that exist only in theories like the seesaw mechanism for neutrino mass, were created in asymmetric amounts. These particles then decayed, and because of CP violation, they decayed in ways that produced slightly more leptons than antileptons. Leptons are the family of particles that includes electrons and neutrinos. Through a process called Sphaleron transitions, a kind of quantum mechanical reshuffling that only happens at extremely high temperatures, this leptonic asymmetry was then converted into a baryonic asymmetry. More protons than antiprotons, more neutrons than antineutrons. The tiny excess of matter over antimatter that eventually became everything. It's a beautiful theory. It's mathematically elegant. It connects the mystery of the matter-antimatter asymmetry to the mystery of neutrino mass. But it operates at energy scales of around 10 to the power of 15 GeV, roughly a billion times higher than what the Large Hadron Collider can reach. It may be untestable directly, in any laboratory, by any machine humans could realistically build. We may never be able to confirm or deny leptogenesis by direct experiment. We would have to find its fingerprints indirectly, through its consequences, like the spectrum of gravitational waves from the early universe, which future detectors might be able to measure. Another class of theories involves something called baryogenesis at the electroweak phase transition. This is the idea that the matter-antimatter asymmetry was generated not at the very highest energies right after the Big Bang, but slightly later, at a moment about 10 picoseconds after the Big Bang, when the universe cooled enough for the Higgs field to switch on and give particles their mass. This phase transition, the electroweak phase transition, could have been a violent, turbulent event with bubbles of the new, broken symmetry phase nucleating and expanding through the universe like bubbles in boiling water. At the boundaries of these bubbles, the intense heat and quantum fluctuations could have generated the matter-antimatter asymmetry. The appealing thing about this theory is that it happens at energy scales that are within reach of future particle colliders. The measurement of the Higgs boson's self-coupling, which will be a major target of the high-luminosity LHC and future colliders like the proposed FCC or CLIC, could reveal whether the electroweak phase transition was the violent, first-order kind needed for baryogenesis. Then there is the possibility that the answer lies in an entirely different type of particle, one predicted not by the standard model, but by its most popular extension, supersymmetry. Supersymmetry, or SUSY, is a theoretical framework that proposes that every particle in the standard model has a heavier superpartner. The electron has the selectron, the quark has the squark, the photon has the photino. These superpartners could have played a role in generating the matter-antimatter asymmetry. Supersymmetric theories also often solve other problems in physics simultaneously. They provide a natural candidate for dark matter. They help stabilize the mass of the Higgs boson against quantum corrections, and they allow the three forces of the standard model to unify at high energies, a beautiful feature known as gauge coupling unification. The Large Hadron Collider has been searching for supersymmetric particles since it turned on. So far, it has found nothing, which doesn't mean supersymmetry is wrong. It means if it exists, the superpartners are heavier than the LHC can currently reach. Future colliders with higher energies might find them, or they might not. And here's where the picture gets truly vertiginous. Because the matter-antimatter problem is not the only profound mystery lurking in the structure of the universe. It sits alongside other deep puzzles: dark matter, dark energy, the cosmological constant problem, the hierarchy problem, the information paradox of black holes, all of which suggest that our current understanding of reality is radically incomplete. The standard model and general relativity, the two greatest pillars of modern physics, are both spectacularly successful in their respective domains. But they are known to be incomplete, possibly even mutually inconsistent at the most extreme scales. The universe is telling us, through these mysteries, that there is an entirely new layer of reality waiting to be discovered. And the matter-antimatter problem might be the thread that, when pulled, begins to unravel that deeper picture. Let's talk about something that makes the antimatter mystery even stranger. Because it's not just that matter and antimatter should have been created equally. It's also that antimatter is almost completely absent from the observable universe. When we look out at the cosmos with our telescopes and detectors, we see a universe made almost entirely of matter. The cosmic microwave background, the ancient afterglow of the Big Bang, the oldest light in the universe, shows us a universe in its infancy that was already dominated by matter. The ratio of baryons to photons in the universe is about 1 to 10 billion, and every single one of those baryons is matter, not antimatter. If large regions of antimatter existed somewhere in the universe, we would expect to see a telltale signature, a brilliant glow of gamma rays at the boundaries where matter and antimatter regions met and annihilated each other. Astronomers have searched the sky for this signal. They have not found it. The universe, as far as we can see, is made entirely of matter. This is both reassuring. It means we're not about to encounter an antimatter galaxy, and deeply puzzling. Where did all the antimatter go? Did it simply annihilate with its mirror particles and vanish into photons? Or did some of it escape to regions beyond the observable universe? The evidence strongly favors the first option. The antimatter is gone, destroyed by its own meeting with matter, leaving behind only the tiny, miraculous surplus that became everything we know. Now, at this point, you might be wondering, if antimatter is so rare and so elusive, how do we actually make it? And this is one of the most mind-bending practical realities of modern physics. We make it every day, in hospitals. When you or a loved one has a PET scan, a positron emission tomography scan, A doctor injects you with a radioactive tracer that emits positrons, which are anti-electrons. Those positrons travel a millimeter or so through your tissue before encountering an ordinary electron, and they annihilate. The annihilation produces 2 gamma rays flying in exactly opposite directions, and the scanner detects both simultaneously to pinpoint exactly where in your body the tracer was. Modern medicine uses antimatter annihilation to peer inside the living human body. We are, in a quiet and extraordinary way, harvesting the power of the matter-antimatter boundary every time we perform a brain scan or look for a tumor. At CERN, producing antihydrogen, a complete antimatter atom, requires cooling antiprotons to temperatures close to absolute zero, slowing them until they're barely moving, and then coaxing them to combine with positrons in a magnetic trap. The result is an atom of antihydrogen, which must be kept from touching anything made of matter or it will instantly annihilate. The quantities produced are fantastically small. CERN's alpha experiment, which holds the current record, has trapped antihydrogen atoms for over 15 minutes, long enough to study their properties with real precision. But the total amount of antihydrogen ever produced in the entire history of human civilization wouldn't even make a visible speck if it were somehow converted to ordinary hydrogen. If you wanted to produce a single gram of antihydrogen using current technology, the energy cost would be something in the range of tens of quadrillions of dollars, and the process would take longer than the current age of the universe. Antimatter is the most expensive substance ever made, by an almost incomprehensible margin. This is why the vision of antimatter as rocket fuel, which shows up in countless science fiction stories and occasionally in breathless headlines, remains firmly in the realm of fantasy for now. The idea is physically sound. Matter-antimatter annihilation releases energy with an efficiency of 100%, converting mass directly to energy via Einstein's E equals mc squared, with no waste and no radiation hazard. A matter-antimatter drive, if it could ever be built and fueled, would be the most efficient rocket imaginable. It would make chemical rockets look like children's toys. It could, in theory, accelerate a spacecraft to a significant fraction of the speed of light. But producing even a milligram of antihydrogen, the amount you might need to fuel a small probe, is so far beyond current capability that it might as well be magic. The laws of physics allow it. The engineering does not, at least not yet. Let's zoom back out to the cosmic scale, because there is something else about the matter-antimatter problem that deserves more attention than it usually gets. And that is the relationship between this problem and the nature of time itself. In physics, most fundamental processes are time-symmetric. If you filmed a physical process at the quantum level and played the film backward, the reversed process would also be physically valid. Matter and antimatter, if they are truly perfect mirror images of each other, should make the universe equally valid in forward and reverse time. But CP violation, the tiny asymmetry we've actually measured, implies that time has a preferred direction at the deepest level of particle physics. The arrow of time, that profound asymmetry between past and future that we feel in every moment of our conscious lives, may be rooted in the same physics that determined why matter won over antimatter. The reason time only moves forward might be connected to the reason the universe exists at all. This connection runs deep into thermodynamics and cosmology. The second law of thermodynamics, entropy always increases, disorder always grows, is what gives time its direction in our everyday experience. Scrambled eggs don't unscramble. Spilled milk doesn't flow back into the glass. But the second law is statistical, not absolute. It emerges from the enormous number of particles involved in macroscopic systems. At the level of individual particles, the laws are nearly symmetric in time. The CP violation we observe is a tiny crack in that symmetry at the quantum level, a hint that the universe is not quite time-symmetric even at its most fundamental level. And some physicists believe that understanding the full depth of CP violation, understanding why matter won over antimatter, and understanding why time has a direction are all ultimately the same question looked at from different angles. There's another angle that is even more speculative but profoundly provocative. Some theorists have proposed that the answer to the matter-antimatter asymmetry might lie not in physics beyond the standard model, but in the structure of the universe itself, in the possibility that we live in just one region of a much larger cosmos. In inflationary cosmology, the exponential expansion of the universe in its first moments could have created an enormously large, possibly infinite cosmos, of which our observable universe is just a tiny patch. In some versions of this multiverse scenario, different regions of the cosmos could have different physical constants, different symmetry-breaking outcomes, different ratios of matter to antimatter. Most of those regions would be lifeless. In regions dominated by antimatter, you'd have the same situation as in a matter-dominated region. Antimatter would just be the normal stuff, and matter would be the strange exception. And in the rare boundary regions where matter and antimatter coexisted, there would be nothing but energy and light. Only in regions with a clear matter or antimatter dominance would stable structures, atoms, molecules, stars, planets, life, have any chance to form. This leads to a deeply uncomfortable possibility known as the anthropic principle. Maybe the universe has a matter-antimatter asymmetry not because of any particular physical mechanism that demands it, but simply because universes without such an asymmetry don't produce observers. We find ourselves in a matter-dominated universe because that is the only kind of universe in which beings capable of asking this question can exist. The asymmetry is not explained by physics. It's selected by the existence of observers. This is intellectually coherent, but profoundly unsatisfying to most physicists. It feels like giving up. It feels like admitting that the question has no deeper answer. Most physicists are not ready to concede that. Most believe that the baryon asymmetry is a real physical fact that demands a real physical explanation, and that the explanation is out there, waiting to be found. Let's take a moment to appreciate just how strange and intimate this mystery is. Every single atom in your body, every carbon atom in your DNA, every oxygen atom in your lungs, every iron atom in your blood is a survivor of the greatest catastrophe in cosmic history. It came from that razor-thin surplus of matter particles that weren't annihilated in the first moments of time. You are not just made of stardust, as the poets like to say. You are made of the rarest material in the universe. You are matter that shouldn't exist, animated by chemistry that required billions of years and the lives and deaths of countless stars, walking around on a planet that formed from the debris of those stellar deaths, in a galaxy among hundreds of billions of galaxies, in a universe that had every physical reason to be empty, but somehow, mysteriously, incredibly, isn't. And consider this: the light you see from distant galaxies, the radio waves that carry our television broadcasts out into space, the X-rays that we use to probe the universe's most violent events. All of that is electromagnetic radiation produced by the electrons and other charged particles that survived the Great Antimatter War. Every photon of light carries within it, in a sense, the memory of the moment when matter won. Every time you see something, you are witnessing the aftermath of the universe's most fundamental mystery. The generation of physicists working today is the first generation with the tools sophisticated enough to genuinely probe this question. Experiments like T2K and its successor Hyper-Kamiokande in Japan, like NOVA in the United States shooting a neutrino beam from Fermilab in Illinois to a detector in northern Minnesota, like the Bell 2 experiment at the KK Accelerator in Japan studying beam meson decays, like the LHCb experiment at CERN dedicated specifically to the study of matter-antimatter differences in particles containing bottom quarks. All of these are closing in on the mystery from different directions. The next decade or two could see a genuine breakthrough, a confirmed large CP violation in neutrinos, a discovery of supersymmetric particles that change our understanding of the early universe, a detection of gravitational waves from the electroweak phase transition that tells us directly how turbulent the universe was when baryogenesis happened, Or perhaps the answer will come from a completely unexpected direction, the way so many of the greatest discoveries in physics have. Perhaps some young physicist working right now on an experiment nobody thinks is very important is about to stumble onto the key. Perhaps it's in the data already, waiting for someone to look at it in the right way. Perhaps the insight will come not from an experiment, but from a new theoretical framework that nobody has imagined yet. The way Einstein imagined general relativity, not from data, but from thought experiments about falling elevators and the nature of gravity and time. The universe gave us a mystery worthy of our greatest minds, the mystery of our own existence. The question of why there is something rather than nothing, answered not with philosophy, but with equations and experiments and the patient, relentless work of human curiosity. And here is perhaps the most stunning thing of all. The fact that we can ask this question, the fact that creatures made of matter can peer back through 13.8 billion years of cosmic history and ask why they exist, is itself a product of that primordial asymmetry. If the universe had achieved perfect balance, if matter and antimatter had annihilated each other completely, there would be no atoms, no chemistry, no stars, no planets, no evolution, no consciousness, no questions. The fact that you can feel puzzled or awestruck or humbled by this story is evidence that the universe broke its own rules in your favor. That whatever physics generated the matter-antimatter asymmetry, it created not just matter, but eventually, over billions of years of staggering complexity and improbable fortune, it created minds capable of wondering why. That's not nothing. That might be the most important thing there is. 14 billion years ago, one particle of matter survived for every billion that were destroyed. That particle, or rather, the physics that spared it, eventually led to hydrogen, then helium, then the first stars igniting in the dark, then heavier elements forged in stellar furnaces, then planetary systems, then oceans and chemistry, and the long, slow miracle of life. Then the first creatures to look up at the night sky and wonder, then you, sitting here, inside a universe that according to the most precise theories we have should never have allowed you to exist. You are the universe's most improbable accident and its most astonishing achievement. And the question of why you're here, not philosophically, but physically, at the level of particles and forces and quantum symmetries, remains wide open, waiting for someone exactly like you to help answer it. The search goes on. It goes on in underground laboratories where neutrino detectors wait in utter silence for a ghost to pass. It goes on in tunnels deep beneath the European Alps where protons race toward each other at 99.9999991% of the speed of light. It goes on in offices and classrooms and late-night conversations between people who look at the night sky and feel the full weight of the question pressing on them. Why does anything exist? Why did matter win? Why are we here? These are the most beautiful questions in science. And we are the generation that might finally find the answers. Or we might not. But the search itself, the reaching, the probing, the refusal to accept that we simply cannot know, that is one of the finest things our species has ever done. In a universe that should be empty, we are asking why it isn't. And that, somehow, feels like exactly the right thing to do.